Okay, these are the 6.1 notes, and we're going to be looking at discrete and continuous random variables. So, a random variable is just a numerical value that describes the outcome of some chance process. And the probability distribution of a random variable gives its possible values and their probabilities. So, this shouldn't be anything like too crazy. Book describes it pretty well. Just kind of a definition there. Discrete random variable. A discrete random variable is a variable where we can list all of the possible outcomes. So, for example, we can do this for who wins a game of roulette. Like, you can list every outcome of, like, if I bet red versus black, I know the outcome is either you lose money or you win money, and you can bet the probabilities on the amount you win versus the amount you lose. And you can do this for every type of betting in roulette. You can do this for if you bet like a 1 through 12, and you can bet that you either win $2 or you lose $1, and then you can list the probability of which you win $2, and you can list the probabilities as to which you lose $1. There's only two outcomes, and there's a probability associated with each outcome, and you can list those. Describing the distribution of grades in a specific class. So, for example, in every class, the Prairie School, you can either get an A minus, B plus, B minus. We can go through, we can list every single grade there is. We could theoretically talk about that as percentages, but that kind of starts getting a little bit crazy. If we just think about letter grades, we could assign those letter grades things like 4.0, 3.6, 3.3, 3.0, 2.6, so on and so forth. And that gives a numerical value associated with those letter grades. So that's something that's a discrete variable. And then plenty of other discrete variables out there. How you do in a game of craps, blackjack, etc. We can list the potential outcomes, and we can list the probabilities of those potential outcomes happening. The probabilities for discrete random variables must be between 0 and 1. So each individual probability has to have a probability between 0 and 1. Again, 0 means that it's not going to happen at all. There's absolutely no chance. A probability of 1 means that it always happens. There's always a chance. And then all of the probabilities of all your outcomes have to add up to 1. They can't be short of 1. They can't be above 1. Something has to happen. You've got to have something happening in these discrete variables. So when you add up all of those probabilities, when you add up all the potentials for them to happen, it still has to add all the way up to 1. So you could have 3 probabilities. One could be 50, the other could be, or 0.5, the other could be 0.5, and if that's the case, the last one has to be 0. This is all kind of a mix of things that we've done before. All right, so here we go. This is a pretty straightforward thing. NC State posts grade distributions for its courses online. Students in Stats 101 in a recent semester received 26% A's, 42% B's, 20% C's, 10% D's, and 2% F's. Choose a Stats 101 student at random. The student's grade on a 4-point scale with A is equal to 4 is a discrete random variable X with this probability distribution. So our discrete random variable X is the grade, and then our numerical values we associate with the grade are 0, 1, 2, 3, and 4 for F, D, C, B, and A respectively. So say in the meaning of words what P of X is greater than or equal to 3 is. So this is the probability of the grade being a B or higher. We're saying B is associated with 3, A is associated with 4. We're saying all grades equal to B or better. What is the probability of a student earning a B or better? Well, in that case, this is just like classic probability of A plus B. So we add our two probabilities together here. That's 0.42 plus 0.26. That is 0.68. So that means that there's a 68% chance that if I picked a student at random from this class, that student had a B or better. All right, write the event student got a grade worse than a C in terms of the random variable X. So this would just be P is less than 2. So we're saying grade worse than C. We're not saying grade worse than or equal to C. Since we're only talking about grades worse than C, we only want to look at grades lower than 2. So these are the grades of 1 and 0. We add those probabilities together. This is a 0.12 probability, or again, a 12% chance that if I pick a student at random from this class, they got a grade below a C. Sketch a graph of the probability distribution. Describe what you see. So again, this is kind of going all the way back to chapter 1. So this would be like making a histogram. We've got 0, 1, 2, 3, and 4. And then we can define these 0.1, 0.2, 0.3, 0.4, 0.5. And we're just going to make a rough sketch here. 0 was at 0.2, so it barely rises. 1 is at 0.1 exactly. 2 was at 0.2 exactly. All right, so here we're just eyeballing the graph of this histogram. Obviously, we have some good information here as well. So this is skewed to the left. It has it's one peaked. It's a unimodal graph, but it is skewed to the left because it goes down more towards that side. Most students in this class, we can see that with that 68% probability. Most students are earning B's or better in this class. The median grade in this class is a B as well. You can just think about that and the fact that, all right, if 68% of our students are getting a B or better and only 26% are A, that 50% number, that 50% of the distribution is going to fall in the B range. So that means the median grade is a B of some shape or form in the class. So we can look at this and say that most of the grades in this class are B's or better, and we have a little bit of a left skew as students kind of start getting lower grades. It kind of tapers out in that direction. Now we're going to talk about expected outcome, and to help with the mean, I think it's good to consider the expected outcome. And I've gotten the feedback from you guys that personal stories in these notes that you love them. So we'll go back to gambling. So as I've already told you, I have taken trips to Las Vegas before. I'm a very responsible gambler. I do not encourage you to gamble. I think it is not that much fun. I've done it a few times in my youth as something just to say that I did. Honestly, I've never walked out of a casino with money, so it's not something that I really love. It's something that usually kills about an hour of my time. And there's better ways that you could spend $40 than to just sit there and watch it go away. But with that, I do have two good friends that love going to casinos, and I hate going to casinos with them because every time we go, as always, I have a really hard gambling limit for myself. If I go to a casino, I never, ever, ever bet more than $40. Once my $40 is gone, I'm done. I'm not putting in more money. I'm not putting myself in the hole any bit more. I have my 40. It's done. My two good friends don't live that life by that philosophy. Their limit is $200, so they can play a little bit longer. But I've gone to casinos with them, I'd say 7 to 8 times, and only once have I seen one of them walk away losing the $200. Every other time they walk out, the lowest that they've walked out up, the lowest number I've heard of is $600. That was the first time I went. They usually win somewhere between $1,000 to $2,000 every time I go to a casino with them, and I hate it. Because again, after about 45 minutes, I'm done. And they're walking out with a ton of money. And they only play one game. They only play craps. They don't play anything else. And they always tell me that it's my fault because I'm just choosing not to learn how to gamble and they know how to gamble. But I refuse to believe that, especially now that I'm a statistics teacher. I can tell you that I think that they're just getting really, really lucky and they're not falling for the law of very large numbers. They're playing probably 70 to 80 rounds of craps when they go to the casino. That does seem like a big number, but as we've learned, as we've seen in some of our simulations, 80 can be a small number. 80 might not get us to our true percentage. You can get really, really lucky in those 80 times, and eventually it'll catch up with them in the law of big numbers, but from the times I've gone, they always win, and it frustrates me. So I'll talk about what they always do in craps. They always do this thing called the field. And in the field, you can kind of see these rules here. So in craps, a person rolls 2 dice. And the field is you bet on these numbers. You're betting that it's either going to land on a 2, a 3, a 4, a 9, a 10, or an 11. And then 2 and 12 pay double. So if I bet $1 and it lands on 2 or 12, they give me $2. So I'm leaving the table with $3. If it lands on a 3, 4, 9, 10, or 11, I'm walking away with $1 extra. So I'm walking away with $2. It's a 1-to-1 bet. So let's figure out what is the expected outcome. How much are you supposed to get paid here? Well, there's 3 options here if I bet $1. Either I can lose $1, I can make $1, or I can make $2. Now, I've got the chart here for the sum of when you roll 2 die, what they are. 2 and 12 only is 1 out of 36. There's only a 1 out of 36 chance for both of them. So there's a 2 out of 18 chance. Or there's a 2 out of 36 chance, which is a 1 out of 18 chance that I win $2. Now, 3, 4, 9, 10, and 11 are the other things that win in the field. So I add these up. I've got 5 between 4 and 3. I've got another 5 between 10 and 11. I've got 14. So this is 14 out of 36, which simplifies down to 7 out of 18. And then I can just use simple math to say that there's 10 out of 18 left. So there's a 10 out of 18 chance that if you bet on this in craps, you're going to lose $1. There's a 7 out of 18 chance that if you bet on this, you're going to win $1. And there's a 1 out of 18 chance that if you bet on this, you're going to win $2. So then to figure out what is the expected outcome, what is the expected value of this, what I do is I multiply the amount of money I can make by the probability of it occurring. And I add up all of those numbers together. And I'm actually going to do this as some like fraction math here. So I've got negative 10/18 plus 7/18 plus 2/18. So this is negative 1/18, and this is like 0.056. So this is negative. And that expected outcome means that I'm losing. So if I bet $1, I should expect to lose 5 cents. Well, that doesn't make sense, does it? If I'm betting $1, how am I losing 5 cents? When you can't really lose 5 cents on that dollar. That's not how the game works. That's not an actual outcome. Well, this is because the expected outcome is the same thing, or the expected value is the same thing as the mean. So this is the mean outcome. So let's say that I'm like one of my friends. All I do is I play craps, and all I do is I bet on this value over and over and over again. Well, my average value should be that I've lost 5 cents on every single bet. So if I've done this 100 times, theoretically speaking, I should have lost 5 cents on all 100 of those bets. So I should be down overall $5. I've bet $100 and I'm now leaving the casino with $95. I put a $1 bet on the field every single time, and I just accepted whatever happened. And we're going to say that they're separate $1. Once I bet that dollar, if I put them away, etc., so on and so forth. I should expect to lose about 0.5% of whatever I'm betting in the long term. And the casino knows this. This is how the casino makes their money. They're very, very well aware of the fact, okay, you have all of, like, we know that every single time the average amount of money we're going to make is 5 cents per bet. Yes, there are going to be some times when a person bets $1 on this that we're going to lose money, and that's going to happen frequently, but in the long run, and when we start thinking about like the very large numbers people are betting at casinos and the number of bets that are taking place, like you think of Caesar's Palace in Vegas where they're probably having I don't know, a couple thousand people walk in every single day. So you're talking in the order of 20, 30,000 bets, all more than $1, and they're making 5 cents on every single dollar bet on average. That adds up really, really quick. And that's basically just free money for the casino at the end of the day. The odds are what, so a little Hunger Games reference here. The odds are always in their favor. The odds are never going to be in your favor in a casino. The casinos know this. They're using it, and they know that they're going to make 5 cents on every time somebody makes that bet in craps, and that's just one bet. There are other bets with much worse odds. We could probably look and go through and figure out what the average amount a casino makes on any single bet on any single day, but that's how they make their money. That's how they win. Because if I make that bet 100 times, I'm going to be expecting, on average, to have lost 5 cents on all those. All right. So we've got the mean, the expected value, and you find it the exact way I just did. You multiply that value by the probability of getting that value, and it tells you the mean. And then the standard deviation, just like we've done before, the variance is when you square the value of the true value minus the mean, and then you're going to multiply it, and we're going to multiply it by that probability. So I'm going to show you how to do this on your calculator, but we do want to be able to do this by hand, so I'm going to show you how to do it by hand as well. I know that I didn't go into a huge description there. That's because it's kind of formulas that we've already learned in Chapter 2. We're just adding in a probability to them, and it's just going to be easier to practice it. So a large auto ship dealer keeps track of sales made during each hour of the day. Let X equal the number of cars sold during the first hour of business on a randomly selected Friday. Based on previous record, the probability distribution of X is as shown. So in the first hour, there's a 30% chance that there's a 30% chance a car is going to be sold. There's a 30% chance no cars are going to be sold in that first hour. There is a 40% chance that there's one car sold in that hour. There's a 20% chance there's 2 cars sold in that hour. And then there's a 1% chance that 1 car is sold in that hour. First of all, we want to make sure that this is a real probability. 0.4 plus 0.3 plus 0.2 plus 0.1 adds up to 1. So this is a valid probability chart. Adds up to 1. Every single probability is between 0 and 1, so we're good there. So compute and interpret the mean here. So we've got 0 times 0.3 plus 1 times 0.4 plus 2 times 0.2 plus 1 times 0.1. So we've got, that goes away. We got 0.4 plus 2 times 0.2. I know that that's 0.4, but I'm still using my calculator because, yep. So that's 0.4, and then this is plus 0.1. So this is 0.9. So this means that we are looking at 0.9 cars. So the mean value is 0.9 cars. So that means that we are expecting 0.9 cars to be sold, but that's not what we're saying. What we're saying is, like, over the course of a year, the average number of cars sold in 1 hour is 0.9. That 0 is really bringing it down. That 0 brings it down a lot. When you have 30% of your days where you're not selling a car at all, and then the grand majority of your days you're only selling 1 car, we can look and we can see that those 2 or 3 kind of balance out with the 0. So on the average day, you're going to sell just a little bit less than a car. So you're not always selling a car, but you're getting pretty close to selling a car almost daily via the average. That's what that means. Now, compute and interpret the standard deviation of X. So if we wanted to do this by hand, what we would do is 0 minus 0.9 squared times 0.3 plus 1 minus 0.9 squared times 0.4 plus 2 minus 0.9 squared times 0.2 plus 3 minus 0.9 squared times 0.1. All right, so we'll go ahead and we will get all of these values squared. So this is 0.81 times 0.3. It's 0.01 times 0.4. 1.21 times 0.2. 4.41 times 0.1. 0.243. 0.41. I apologize. I typed that in my calculator wrong. That did not seem right to me. Check your work if things don't make sense. This is 0.004. This is 0.242. This is 0.441. And we're going to add all those up. This value, 0.93, is our variance. So I'm going to take the square root of that because standard deviation is equal to the square root of variance. So we are looking at the square root of 93.93, and we are looking at a 0.96 standard deviation. So this means that the average value from the mean varies by 0.96. Obviously, that doesn't add up perfectly when we're thinking about it in terms of the number of cars sold. If it's less than 1, obviously you subtract it. You're going to be at 0. You're going to be a little bit less than 0. You're going to sell 0 cars, or you might sell a little bit more, but the standard deviation of that average is 0.96. So we're just looking at that and saying that, okay, that's kind of the average that's the average amount that it varies by from the mean. All right, continuous random variables, not much to go over. The book does a pretty good job of describing this. Make sure you're reading section 6.1 along with this. Continuous random variable is a variable x that takes all the values in an interval of numbers. The probability of x is described by a density curve. The probability of any event under the area of the density curve and above the values of x make up the event. These are events where not every outcome can be mapped. So like heights, weights, because again, when we start breaking that down by especially when we're talking about the full population, it depends on how far you want to measure it out to. We could measure out heights down to tenths of inches. We could measure out weights to hundredths of a pound. We could measure them down to ounces, times of marathon finishes, because we could start talking about again, hundreds or thousands of seconds, especially when we're talking at that Olympic level. So we basically say that each individual event has a 0% probability of happening. What's the probability that somebody finishes a marathon in 2 hours, 1 second, 1.57 seconds? Well, that's a 0% probability, not because it's impossible to happen, but because that as an individual event is pretty unlikely to happen. And that's kind of a matter of how we measure it. So what we do is we say more likely, what's the likelihood of somebody finishing a marathon between 2 hours and 2 hours and 2 minutes? We can look at that chunk of time and we can say, okay, based off the number of people who have finished a marathon, average marathon times, so on and so forth, here's the probability that they finish in between that time. Or what's the probability a person finishes a marathon between 3 hours and 3 hours and 15 minutes? That's a much larger area, and we're going to look at a density curve, and we're going to figure out the area under the density curve. So this works the exact same way of what we did in chapter 2. In chapter 2, when we were looking at those normal curves, when we were looking at density curves and figuring out what is the area under a density curve, that's what applies here. So Exact same scenario, looking at those density curves, being able to figure out the area. Now we're just going to add in new and better language when we're talking about those probabilities. All right, you guys got a homework assignment tonight. Go ahead, work on that. If you have any questions or concerns, please reach out as soon as possible, and have a great night.